Good day. On this video, we are going to have the experiment number 1 that we are going to have for electric potential. So we are going to deal with this FET Colorado simulation so that we are able to understand the electric potential of a point charge and the electric field and how we are able to see the relationship of electric field, voltage, and the distance. So let me share with you the procedure of this activity. So we have here the procedure. So number 1, open the electric field simulation, turn on the grid and show numbers, and place a positive point charge of 1 nanocoulomb at the center of the grid and make measurements of number 2, make measurements of electric potential and the magnitude of the electric field at the following points to the right of the point charge. Use the voltmeter to measure the electric potential, and then the meter measures the electric potential at the point where the center of the cross is located. Be sure that to put the units for E for the electric field and for the V. So here we are going to calculate for the magnitude of the electric field. You record your observation on the table of this activity sheet. Let's take note that the equipotential lines are lines with equal electric potential. And using the plot tool that comes with the voltmeter, we will make 2 equipotential lines at distance 0.5 meters and at distance 1.5 meter. Then we will enable the electric field vectors in the simulation and put an electric field sensor at different points on the equipotential and note the direction of the electric field vector that can be concluded. And we will answer the question, what can you conclude about the direction of the electric field vector in relation to the equipotential lines? While I am doing the activity, you need to take a snapshot of the simulation showing the equipotential lines and paste it onto the Word document for your submission. And then number 6, use the electric field sensor to investigate points in between the 2 equipotential lines. Thus, the electric field vector point toward the higher electric potential and towards the lower electric potential or along an electric potential line. Using your data from question number 2, you plot the electric potential versus the distance in an Excel file. And then this will be called as the potential graph. Then you label your graph in axis and include units. Copy and paste your graph along with any fitting you have done to test the hypothesis in your Word document. So I will show you the data sheet that we need to answer. So we have here the distances. This might not be the correct value that I'm going to have. A little later, I will show you what will be the distances that you are going to write on this part. Then we will calculate for the magnitude of the electric field. And then we will going to measure the electric field potential so that we are able to calculate for the electric field intensity or the magnitude of the electric field. Then you will answer the guide questions and you need to summarize the relationship as for conclusion of the electric field and electric potential. Okay, so let's go on now to our simulation care of the petcolorado.edu. So we would like to thank the Pet Colorado for coming up with this very good simulation in over the internet. So we have here to place a 1 nanocoulomb charge. So we turn on the grid first. So we are going to place it on the middle. part of our field. Then we click the values, the voltage. You notice that the voltage here is the one that with the red color. And then we will place the electric field. So you will notice that electric field lines is our vectors, is electric field lines that is moving infinitely outward of the positive charge, while the negative one, so from infinity moving to the negative charge. So that's the relationship of the positive charge to the negative charge if we talk about electric field intensity. So it's moving out for positive and moving in into the negative. So this is not what you're going to do. So we need to place this meter, this pull push rule, a virtual pull push rule, where we are able to measure distances where we will place our meter, this voltmeter here. So the first one is at 50 centimeters. So it's very difficult to come up with the exact value. So we're going to use 50.3 centimeters or 0.503 meter. Again, that's 0.503 meter. Let's take note that we need to have a calculations or values for the distances in meters. So we are going to look into what will be the voltage or the electric potential at 0.503 meter. So we have here the voltage is equal to 18.08 volts. Okay, so that is for 0.503 meter. Okay, so let's move to the next distance. We will have 100 centimeters, or hope we get 100. If not, okay. We are going to use 100.7 centimeters or 1.007 meters. So the voltage or the electric potential now is equal to 8.986 volts. Okay. Then we have 150 centimeters. $150, please. So I have 150, then we will use 150.5 or 1.505 centimeters. Okay, so the electric potential is equal now to 5.979 volts. Again, the electric potential is equivalent to 5.979 volts. For our next distance, we have 200 centimeters. So we have 200.3 centimeters or 2.003 meters. 2.003 meters. And the electric potential is equivalent to 4.507 volts. And then we have 2.5 meters or 250 centimeters. So we have the exact distance, 250 centimeters or 2.5 meters. Okay, so the electric potential now is equal to 3.599. That's 3.5 volts. So what will be the magnitude of the electric field? So that's what you're going to calculate. Next, we have 300 centimeters, sorry. So that's 300 centimeters. So we can have it. So we will use 3.004 centimeters. So our electric potential is 3.001 volts. Our electric potential is 3.001 volts. So again, what is the magnitude of the electric field? If we have an electric potential of 3.001 and a distance of 3.004 meter. So let's move on now to the next. So we're done with the data table. So here, please. So we are going to look back. So if we place our sensor here, that's 33.6, the farthest with the yellow. So 30.6, then the nearest along the equipotential line, 43.3. So when we move, so you will notice it's playing with the same. So when we move around, we'll still get this almost the same value since it's on an equipotential line. Then if we place our sensor on a 1.5 mark, so you will notice that it will have an average for almost the same value for the magnitude of our electric field. It's much lesser compared if we place our sensor at 0.5 meter mark. So there is just a varying since it's not moving on a perfect circle. Our equipotential is perfect circle, but the way I move the sensor is not on a perfect circle. That's why there is a variation, a slight variation on the value of our electric field. Okay, so that's it. I hope that you are able to capture the things that you need to capture, and then you're able to get the right data for you to calculate for the magnitude of the electric field on the data sheet. Thank you very much, everyone, for listening and for viewing this video. See you next time. Goodbye.